8.1. In this lesson, we're going to be talking about quadratic functions. So if you look at your handout, a quadratic function is a nonlinear function that can be written in the standard form y equals ax squared plus bx plus c. In this form, a is not equal to 0, and the u shape of the graph of a quadratic function is called a parabola. So you'll notice right here, this little shape here, this is a parabola. Couple of characteristics that we have with our quadratic functions. You're going to notice that we have a vertex. So right there, talking about vertex. And it says the lowest point on a parabola that opens up or the highest point on a parabola that opens down is our vertex. So for this graph right here, this one opens up. So notice that those arrows are pointing up. And the vertex for that one is right down here at 0, 0. We also have something called the axis of symmetry. And if you remember, symmetry means that I could take a shape, fold it in half onto itself, and you'll have the exact same thing on the left side and the right side. So they'll join up right together when you fold them on that line. So the axis of symmetry for this graph is right here. You see this dotted line? That's our axis of symmetry. So if I were to fold on that dotted line, this side of the parabola will lay perfectly onto this side of the parabola. So when they did this axis of symmetry, notice that it happens to be right there on that y-axis. So if we're looking at the equation for our axis of symmetry, it is that vertical line right there at x equals 0. So if we're talking about parabolas and we have our axis of symmetry, it's going to be that vertical line where the two halves will fold and touch one another. So this one, if I'm writing a line or an equation for a vertical line, it's always going to start x equals. So x equals 0 was that axis of symmetry. So we're going to take a look at this graph here, and we're going to jot down some characteristics about it. So if I'm looking at this right away, thinking about my domain, remember domain is the x-axis, those values. So as I look at this graph, if I were to continue it, it's going to continue to stretch up and out to infinity. So if I'm thinking about that, that means that every possible x value could be plugged into my equation that they gave us right here and give us a result that would end up on our graph. So for our domain, we're going to say that it is all real numbers. We're just going to abbreviate that. Now for the range, if I notice, I've got these arrows pointing up. I'm going to go up to infinity this way. I'm going to go up to infinity this way. But I do have a limit down here at the very bottom. So it looks like there is, once it hits this point right here, it turns and goes right back up. So the limit for my range is the fact that I can have all real numbers, but they have to be greater than or equal to -4. So that y value, remember looking for the range, the y value is this spot right here, which is greater than -4. So 1, 2, 3, 4. That's how we knew it was -4. So all real numbers greater than or equal to -4. All right, so the next one we're going to talk about, when is the graph decreasing and when is it increasing? So remember, when we're talking about increasing and decreasing, we're reading our graph from the left to the right. And if I read my graph from left to right, in this direction here, it's going down. And then it starts to curve right back up. So I would say it is decreasing until I get to this spot right here. And this spot for the decreasing, remember when we're talking about increasing and decreasing, I'm looking at the x values. So once I get to the x value of -1, that's when it kind of transitions and starts to increase. So I'm going to say that it is all of those x values less than -1. Now remember, it can't be equal to -1 because right at that one spot right here where x is equal to -1, it's not increasing and it's not decreasing. That's the spot where it kind of transitions from one to the other. So for increasing after that, so all the values greater than -1 are going to give us an increasing section of our graph. So x is greater than -1. Now we're looking for our y-intercept. So I look at my graph. Where does it touch the y-axis? It touches right here at 1, 2, 3, -3. So our y-intercept is -3. Then I'm looking for my x-intercepts. Where does it touch the x-axis at? So I've got a spot here, but I notice I also have a spot here. So this one touches the x-axis in two places. We see that it is 1 to -3, as well as +1. So -3 and +1 are where it touches the x-axis. The next section we're talking about is positive and negative. Remember, positive and negative is talking about above the x-axis or below the x-axis. That's when we're talking about it being positive or it being negative. So when I look at my graph, I notice that this section of the graph is positive. It's above 0. But this section's also above 0. So that's also positive. So I have two sections for when it's positive. So I know that it's positive when all of the values for x are less than -3. So it's positive when x is less than -3, but it's also positive. Notice right here, if I continue on, right, these x values that I'm plugging in, if I plug in any values that are greater than +1, I'm also going to continue to get positive y values. So I have x is greater than -3, or sorry, less than -3, and x is greater than +1. So you'll notice it kind of coincided with those x-intercepts, right? Because that's where it transitioned from being below the x-axis to being above the x-axis. But we also have to talk about when it's negative. So if I look here, this entire loop here, kind of skip over that little green dot. There we go. This entire section down is below the x-axis. So this entire section of the graph is negative. And what that means is all of the values between x is -3 and x is +1, all of the values in between there are negative. Now, again, it's not equal to -3, it's not equal to +1, because those are the spots where it's neither positive or negative. They're right there on the x-axis. So it's between x is -3 and x is +1. So -3, x is going to be greater than -3, but it's going to be less than +1. So less than +1, greater than -3. And again, we're talking about those x values that we're plugging in, giving us negative y values. And then last for this graph, we're going to talk about that end behavior. So as as y goes to positive infinity, so as this y value goes to positive infinity, what is happening to our x values? We have that x is going to negative infinity. So x is going to negative infinity, y is going to positive infinity. So y goes to positive infinity as x goes to negative infinity. So again, for this one, we're traveling on the left side of our graph. So as our x values are going to negative infinity, our y values are going to positive infinity. And we also have to talk about the other side of our graph. As our x values are going to positive infinity, our y values are still going to positive infinity for this graph. So y goes to positive infinity as x goes to positive infinity. All right, so just a couple things that I want you to take a look at the bottom of your sheet here. It just kind of gives you some examples of a parent function as well as some additional functions. So looking here, this middle graph here on both of the drawings, those are the parent function. So we're just kind of tracing over those. And then we have, I'm going to use green on the inside. Whoops. Of course, I would loop two of them. Okay, let's fix this. I snagged the wrong side of this line here. All right, so there's that one. And I'll draw over top of this middle one better with the green one. There we go, fixed it. So the middle one is the green one, or sorry, the inside one is the green, the middle is the blue, and then I'm going to use red for the outside. It's a lot easier to see. Oftentimes when we're looking at comparing, we're going to be comparing to this blue parent function here because that's the function f of x equals x squared, and that's going to help us to draw some conclusions about other graphs. I'm going to do green on the inside for this bottom one as well. And then red for the outside. That way you can kind of see more clearly what we have here. So it kind of gives you some scenarios. So for this left side, it says f of x equals ax squared when a is greater than 0. So when a is greater than 0 but less than 1, the graph f of x equals ax squared is vertical shrink of the graph. So it's making it shorter vertically, which means that it is wider. When a is greater than 1, the graph of f of x is a vertical stretch of the graph. So it's making it taller, which is making it thinner. So the green one is this bottom, and the top one is the red. And then same idea over here. So when a of x squared when a is less than 0, so notice it's flipped our graph, so it's the same thing, but it's just flipped over. When negative a is greater than -1 but less than 0, the graph of f of x is a vertical shrink with a reflection in the x-axis of the graph. So it's flipping it over. That's what the negative does to us. And then it stretches it out here. So this is our red one. And then when a is greater than -1, the graph of f of x equals ax squared is a vertical stretch with a reflection. So again, it's reflecting and it's shrinking it like horizontally, making it look tighter together, but it's longer. So it's like I took a picture on a computer and like I took that one side and I stretched it down. So it makes it thinner looking, but it just makes it longer. So that's this one right here. All right, so let's take a look on the back side here at example 2. So for this one, we've got g of x equals 2x squared, and we're going to compare it to the graph of f of x equals x squared. So let's draw that one out first. And I'm going to use my blue marker just to kind of keep consistent with the drawings on the front. So if I were doing f of x equals x squared, well, if I plugged in 0, 0 squared is 0. If I plug in 1, 1 squared is 1. If I plug in -1, -1 times -1 is also +1. If I plugged in 2, 2 squared is 4. -2 times -2 is also 4. And 3 squared is 9. Negative 3 squared is also 9. So that'll give us a few dots on here. Get that parabola shape. All right, so now we're going to make our table for g of x. Just do this so we know which one was the blue one. All right, so for g of x, let's just use green for this one. Here's our little table, x and y. Remember that when I'm plugging in a value for x squared, the entire x value is what is being squared. So notice when I was talking about the negatives here, I did -1 times -1 because I plugged it in and the entire x is squared. So it's essentially like having parentheses around that negative number. So if I were picking some values, I'm going to use -2, -1, 0, 1, and 2. So -2 times -2 is +4. +4 times 2 is 8. And it's going to be the same for my +2, right? +2 times +2 is 4. 4 times 2 is 8. And you kind of notice that we've got those matching patterns on each side. If I'm plugging in -1, so -1 squared is 1, times 2 is 2. +1 times +1 is 1, times 2 is 2. 0 squared is 0, times 2 is 0. So we're going to go ahead and plot those points. So I've got 0, 0. I have -1, 2. And I have 1, 2. I have -2, 8. And +2, 8. So if I'm looking at these things and I'm comparing the two graphs, I'm going to notice that they're both opening in an upwards direction. So both open up. I notice that they have that same vertex. And that vertex is 0, 0 for this graph. I notice that they have the same axis of symmetry. So notice if I folded them right here on x equals 0, they would both have spots that touch up perfectly with the other side. So same axis of symmetry. And as we mentioned, that would be x equals 0. I do notice something different about them is that the graph of g of x is narrower than the graph of f of x. I'm going to put this here so that we remember that that's the color we were using. So our graph of g is narrower. Oops. Narrower than f. And that's because g is a vertical stretch of the graph for f, and it's a stretch of a scale factor of 2. So notice I multiplied x squared by 2, so my scale factor was 2 for that one. So it's narrower than f because g is a vertical stretch by a scale factor of 2 of the graph of g of f. So it's narrower than f because g is a vertical stretch by a scale factor of 2 for the graph of f. All right, so let's take a look now at example 3. So we're going to be comparing again with our parent function f of x equals x squared. So we're going to go ahead and jot a couple of those points on here. Notice we have a little bit different section of our graph, but that blue is still going to start at 0, 0. We have our point 1, 1, negative 1, 1, and then we have 2, 4, and negative 2, 4. So there's our parent function that we're going to use as we start to compare with these. Now, we're going to make our table for this next function here. I'm going to go ahead and give it a color since I'm already holding those. There we go. So H is going to be green again. So for this one, I'm noticing there's a fraction, right? If I want to make my life a little bit simpler, I'm going to be using things that are going to multiply nicely with my fraction. So the values that I chose are negative 6, negative 3, 0, 3, and 6. Sometimes you'll have a graph that will work out fine if you end up with fraction answers. This is going to give us some whole number answers. And it really just depends on the graph that you're given or the graph that you create for yourself. So if I'm plugging in, negative 6 times negative 6 is 36. 36 times negative 1/3. So it's like 36 over 1 times negative 1/3. Remember, that's going to give me negative 36 over positive 3. So negative 36 divided by 3 is negative 12. So I've got negative 12 for negative 6 and also for positive 6. Because again, if I square positive 6, I get positive 36. So then I've got negative 3 squared is positive 9. Negative 1/3 times positive 9 gives me negative 3. Same with positive 3 being negative 3. 0 squared is 0. 0 times 1/3 is 0. So we've got negative 6, so 2, 4, 6, negative 12. And I also have positive 6, negative 12. Negative 3, negative 3, so 1, 2, 3. Positive 3, negative 3, 1, 2, 3. And we've got 0, 0. All right, so comparing these right off the bat, I notice some differences about them. But let's start about some things that might be the same. So I noticed that they do have that same vertex. And the vertex, again, is 0, 0. It won't always be that, but for these ones it is. I know that they have the same axis of symmetry. So the same axis of symmetry. And that is, so it goes right here where it can fold onto itself. So that would be x equals 0 for that axis. We also notice that, so for some differences, f of x still opens up, but h of x is opening in a downward direction. So h opens down, and notice how it's wider as it opens down than our f of x is. So h opens down and is wider than f. So what that means is that h is a vertical shrink. So basically we took this and we shrank the sides in. So vertically we went like this, and it makes it spread out to the side. So when you take it and you go like this, it makes the picture kind of look like it's spreading out, right? So H is a vertical shrink. Another way to tell that is notice that this is a fraction. When we had our vertical stretch on example 2, we had a 2x, which was a whole number. It was greater than 1. And here we've got a number that's less than 1. And so that's going to give us a vertical shrink. And the scale factor of 1/3. And it's a reflection. So notice that we flipped it over that x-axis there. So reflection over the x-axis. Slide that up a little bit. Of graph F. I know some of you might be thinking, well, if it's a reflection, shouldn't it be exactly the same? Basically what it is the negative makes you reflect it over, and then the 1/3 made it look like it's spreading out, because we kind of, if we were thinking about pictures that you drag and things like that, if I take the corner, it goes proportionally. If I just take the corner and I push it up, it makes the picture look squished, like it's stretched out a little bit sideways. If I had grabbed the bottom and I pulled it down, it makes it look like it's really thin and kind of smushed in sideways. So fractions shrink and the negatives flip. That's something that you want to kind of note to yourself. So the negative sign flips it, and fractions shrink.